We're going to talk about the periodic table today. What you see here is the periodic table as we know it today. It has 118 elements. Okay, since science has come a long way since Aristotle, a philosopher, thought of our elements as air, fire, water, and earth. Since then, scientists have identified 90 naturally occurring elements and have created about 28 others, giving you a total of 118 elements. That's how many elements we have discovered here on Earth. There may be more out in space, but this is what we have. This is our current understanding today. So why is the periodic table so important? Well, first of all, a periodic table organizes your elements in such a way that you can get a lot of information about the element just by noticing where it is located in the periodic table, its position in the periodic table. We already know this. We already have talked about how you can find the orbitals your electrons reside in by looking at the periodic table. But that was just a happy result from the arrangement of the periodic table, because orbitals came much later. The periodic table is organized in such a way that you can get lots of basic information about those 118 known elements. You may know nothing about element number 117, but knowing where it's located on the periodic table will tell you a little bit about how it behaves and how it looks. So it's important to understand the organization and the plan for the periodic table to get that basic information. So let's talk about the history of the development of the periodic table. So we're going to start off after Aristotle, and we move to scientists. We're going to move on to Antoine Lavoisier. He was the first scientist to compile a list of known elements back in the late 1700s. So he would study the world around him, and he's like, we know about these different elements. And you know what? Element A is very similar to element B. So he'd start writing these lists and he would compile them and kind of put things that behaved in similar fashions near each other. But they weren't organized in any other way other than a list. Along comes the person we call the father of the periodic table, and that's Mendeleev. Mendeleev, he created the first accepted version of the periodic table about 80 years after Lavoisier had his lists. Okay, the periodic table he developed is not the one we use now, but it was a precursor that led to where we are now. And he grouped his elements according to increasing atomic mass, how much they weighed. Now our periodic table is not arranged that way. Now it's arranged by atomic number. But he organized it according to our increased atomic mass. And the way he organizes predicted the existence and the properties of undiscovered elements. But anytime they discovered an element, they would have to adjust the table. Okay, so this is what the periodic table looked like for Mendeleev. It's a little different than the one we have right now. First of all, one thing you notice, helium, neon, argon, krypton, xenon, and radon, which we've talked about those being your noble gases. They're on the left side of the periodic table. We now have them on the right side of the periodic table. Right here, these guys. These are part of that D block on the periodic table, like in the middle, but here they're kind of pushed off to the right. But then you have things like silver and cadmium and gold and mercury that belong with these guys, but they're over here. So there's a couple of differences to keep in mind. Okay, after Mendeleev, this is 1869. Well, before we move on, I just want to show you did by increasing mass number. So if you look at your periodic table and you look at element number 26, which is iron, element 27, cobalt, element 28, nickel, element 29, copper. If you look at their atomic masses, iron is 55.845. Remember, he did by increasing atomic mass. Okay, cobalt is 58.933, so that's higher, so we're still increasing. But the nickel is slightly lighter than cobalt, and that has to do with how the isotopes are distributed. So in Mendeleev's periodic table, cobalt and nickel were swapped with each other. Nickel was first, and then cobalt. Now that we have it arranged in a different manner, it is arranged with cobalt first and then nickel. So that brings us to Moseley. Moseley in 1913 observed and measured X-ray spectra using X-ray radiation, X-ray light wavelengths, and he measured the spectra of many different metals, and he realized that grouping the elements on the periodic table by mass was kind of arbitrary. There was no reason to do that. There was no similarities between the elements that were grouped together, other than the fact that they kind of weighed the same amount. And what if you found something kind of in the middle between them? You'd have to adjust things. This is around the same time when the proton, electron, neutron, nucleus, all that was being discovered. So at this point, he realized, wait a minute, every element contains a unique number of protons. So why don't we arrange by protons? Since every element, that's its calling card, its ID is the number of protons. Why don't we arrange by the number of protons or by your atomic number? And in doing so, that allowed him to leave holes in the periodic table for elements that had yet to be discovered. So he realized that there was missing elements. When he did it by the atomic number, they left those holes so you can go back and fill it. So if you find an element that has 116 protons, and then you have one that's got 118, you can still leave that space for one element, that element 117. Which leads us to the periodic law. And what the periodic law says is that there is a periodic repetition of chemical and physical properties of the elements when they are arranged by atomic number. What this means is if you're arranging your periodic table, if you're arranging your elements just by atomic number in a one big long line, what you would see is a pattern that repeats, called the periodic law. A pattern that repeats in terms of physical properties and in terms of chemical properties. And Moseley realized this, and he said, "I'm going to um, manipulate or take this into account when I'm putting my table together. Why don't I put things that are repeating near each other, one on top of each other?" And that's what he did. All elements on a periodic table have a symbol that is unique to them, that is used across the world. So for instance, carbon's symbol is C. It may be called carbon here, or it might be called carbono somewhere they speak Spanish, but the symbol everywhere you go will be C. Usually your symbol consists of a capital letter, single capital letter, or if you have more than one letter, the first letter will be capital and any of the remaining letters will be lowercase. For instance, copper is a capital C and a little u. Because it is got two letters, the second letter must be lowercase, the first letter must be capitalized. If you were to write it both capital or both lowercase, that would be wrong. Cobalt is capital C, little o. That means cobalt. But if you have a capital C and a capital O, then that is carbon monoxide, which is not on the periodic table. It is actually a chemically combined compound. Okay, some common elements you will be using this class, just so you kind of hear them. We have sodium, Na. We use this a lot. It's on the left-hand side of the periodic table. Third energy level is sodium. It's one that we'll use a lot. We'll use chlorine a lot. Chlorine is second to last column on the right. Chlorine is down there. That's called a halogen. We have carbon and cobalt, neon. Now, if you look at gold and silver, they've got little funny symbols, Au and Ag, but more importantly, look where they are on the periodic table. Gold has a atomic number of 79 and silver is right above it. And above that is copper. These are all things that we use to make jewelry, gold being more valuable than silver, and silver being more valuable than copper. But they all react in a similar fashion, in that they don't really react, which is why they're so valuable. Is because they don't react. So when you make a necklace of gold in 15 years, it will still be gold. It won't have tarnished. So we have oxygen. For O, we use that a lot. Potassium, we use that a lot. K. Iron, Fe. Iron is a transition element. It's in that D block of the periodic table. Mercury, Hg. It is one of two liquids on the periodic table. These are just kind of common elements and their symbols. Okay, now we're going to talk about valence electrons. Valence electrons are the electrons that are on the outermost energy level of an atom, the ones that are on the outside, not the ones on the inner energy levels, but the ones on the outside. So if you were to write the electron configuration of an element in its noble gas configuration, it would be everything that comes after the noble gas. I shouldn't say everything. It would be all the S's and P's that come after the noble gas. Okay, so what you have here you have what's called two halogens, things from the second to last column. The way I know it's a halogen is it has 7 electrons. 7 electrons. Okay, but if you notice, these guys want to be paired up, 2, 2, and 2. An s orbital and 3 p orbitals for a total of 8. But this one only has 7, and this one only has 7. So there's space for a reaction to happen, for another electron to come in to make it happy. Okay, so your valence electrons are the only electrons that matter. They're the ones that do the chemistry. So if you were to look at this, if you look at this electron here and this electron here, what happens? What happens is that they kind of come together to make a molecule. This is probably like fluorine or bromine or chlorine or something like that. Things that have the same valence electrons have similar, not identical, but similar chemical and physical properties because they have the same number of electrons, valence electrons, to do the chemistry. Okay. These are the electrons, again, in the outermost energy level of an atom. So what does that look like? So let's look at potassium. Potassium has 19 protons. That means it has 19 electrons. So if we were going to put our electrons on this Bohr model of potassium, the first circle would be your first energy row. The second one would be your second energy level. The third one would be the third energy level. The fourth one would be the fourth energy level. So if we were to look at putting our electrons on here, this is our electron configuration. We would put 2 in the first. That's the 1s2. We have a total of 19. We would put 8 on the second energy row. That's 2s2, 2p6. 2 plus 6 is 8. So if you count, there are 8 around there. Now, this is our 3s. We can put 2 electrons there. Okay, and now we have to put our 3p6. So we have add those there. Now we have 8 in the third energy row. And now we're going to look at so those guys are completely full. There's no more room for any electrons. Now we have 1 electron left. That's in the fourth energy row. This is your valence electron. That is the electron that is important. So if you write the same electron configuration in terms of its noble gas configuration, it's what comes after the noble gas. So the 4s1, 1 valence electron. Potassium has 1 valence electron. Okay. Things that are in the same column on the periodic table have the same number of valence electrons. For instance, lithium and potassium are in the same column. Lithium has 1 valence electron. The number of electrons on the outside shell has 1. But it only has 2 energy shells. But we only care about this electron, the one on the outside. Potassium, we already drew before, has 4 energy levels, but only 1 electron in the outside shell. They have the same number of valence electrons. Okay, so to remind you, your valence electrons indicate the row of your periodic table tells you what energy level you're on. If you're on the first row, you're in the first energy level. Second row, you're in the second energy level. Third row, you're in the third energy level. Okay, we're looking for your S's and your P's in the highest energy levels, not any D's, S's and P's. Okay, those are your valence electrons. The goal for these guys is to have 8, but sometimes they don't have 8, and the way they get 8 is by doing chemical reactions. Our one exception is helium. Helium is in the first energy row, but it only gets 2 electrons. Okay, so you should label your periodic table. And to label a periodic table, it will look like this. Okay, this is what your periodic table looks like. You should have it all colored because we did that previously. But if we were to label our periodic table, we're looking at the things that are blue The things that are blue on this periodic table. Okay, we're looking at the blue things on the periodic table. Everything in this column right here, this very first column, has one valence electron because it has a 1s1 or a 2s1 or a 3s1 or a 3s2. Everything in this column right here has two valence electrons. We're going to skip over the D's. We're going to come over here to the P's because your valence electrons have to do with s and p orbitals. Everything in this column has three valence electrons. 4, 5, 6, 7, 8 valence electrons. With the exception of helium, helium only takes 2 valence electrons. So let's do that again. Everything in the first column, 1 valence. Second column, 2 valence. Third column, over here, group 13, 3 valence, 4 valence, 5, 6, 7, 8. You should label your periodic table to put the number of valence electrons there. Your D's and F's have a different number of valence electrons depending on the situation, and we would have to tell you, but typically they have 1 to 2 valence electrons. Okay, so now what we're just demonstrating here is what's called our electron dot structures. Remember, everything in the first column has one valence electron, one electron that can do chemistry, one electron on the outside shell. So if you were to write the electron dot structure, you would write its symbol and then one dot for an electron. A dot means an electron. Lithium, same thing. One dot, the symbol, and then one dot. Sodium, symbol and one dot. Potassium, symbol, one dot. If you look at the second group, the second column, it has 2 valence electrons. You know that because you labeled your periodic table, but just in case you don't remember that, because you have a 2s2, that's 2 electrons. So if you were to write that, you would write 1, 2. Magnesium, 1, 2. Calcium, 1, 2. Don't pair up until you have to because of Hund's rule. Okay, if you go all the way to the P block, let's look at boron or aluminum. That has 3 valence electrons. So you put those electrons around it. 1, 2, 3. 1, 2, 3. Carbon has 4 valence electrons. 1, 2, 3, 4. Nothing is paired up because it doesn't need to because of Hund's rule. Now we get to nitrogen. Nitrogen, you're going to have to start pairing up because there's no other spot for them. It's got 5 valence electrons. 1, 2, 3, 4, and now pair up. 5. Same thing with phosphorus. Oxygen has 6. Fluorine and chlorine have 7. And then you look at your noble gases. Your noble gases have 8 electrons around them. That makes them happy. That's what they want. That's what all elements want. They just want to have an octet. One exception, again, is your helium. Your helium only gets 2 electrons because it's in the first energy row where there's only s orbitals available. So its electron dot looks like this. And they're paired up because you filled up your s orbital. They're paired up in an s orbital already. Okay, let's talk about periodic table activity. Okay, what is it? Let's describe what our periodic table looks like. This is our periodic table of elements. So we're going to talk about all the different parts. So one thing you should have noticed from the last, when I displayed my periodic table, is that there's columns and rows, right? And you can see it here also. When we're talking about a column, something that goes up and down, that is called a group or a family. Things up and down are a group and a family. So like lithium, sodium, potassium, rubidium, those are all part of a group or a family. And just like in a family, elements within a group look similar. They have similar physical properties and they have similar chemical properties. They act in a similar fashion. They're being raised by the same sort of parents. They have similar reactions. Okay, as you go up and down. That's called a group or a family. Okay. If you look at this periodic table, if you look, there's a spot where you've got big red block and a big red block over here. Those are your S's and your P's. We call that the main group of the periodic table, or the representative elements, or the A group. So groups 1 and 2 and 13 through 18 are your main or representative group elements. A group. That's where your valence electrons are. S's and P's. So if I say, what is the representative element in the second group, fifth energy level, you would say strontium. It's the main group. Okay. So again, when you have a group, something like lithium, sodium, potassium, rubidium, cesium, and francium, these guys all have similar chemical properties. Not identical, but similar. In other words, they react in a way that is predictable. We know how they're going to react because they all react the same way. If one is going to react with hydrogen, all of them will, to a certain extent. Okay? It's a predictable thing. They have similar chemical properties and they look similar. Okay, as you go across a periodic table, that's called a period. So you go across a periodic table, that is called a period. And elements within a period do not have similar properties. If you were to look at potassium, which is right here, and compare it to krypton, which is over here, they're in the same period, but they behave very differently. As opposed to lithium and francium, they're in the same group and they behave the same. Your behavior is not the same across a period, but it is the same across a family or a group. Okay, so a period is your horizontal rows. Your physical and chemical properties can change somewhat, but the physical and chemical properties change somewhat regularly across a period. Remember, that's that periodic law where you see a repeating pattern of behavior. Okay, so it's not, so you can see like very reactive, very reactive, not as reactive, not as reactive, not reactive at all. Oh, now we went to something that's very reactive. It's a periodic trend. Okay, elements that are close to each other in the same period are more similar than those further apart. In other words, potassium and calcium, while they're not super similar, they're right next to each other. Potassium has 1 valence electron. Calcium has 2 valence electrons. They have different motivations, but they're much more similar than, let's say, potassium and krypton, which is all the way at the other end. Potassium is a metal. Krypton is a nonmetal. Potassium is a solid. Krypton is a gas. Okay, so let's compare those. Again, just kind of put them next to each other. Your families, your groups are the columns. Those are called groups or families. Within a group or within a family, they have similar, but not identical properties, physical and chemical properties similar. They behave in similar ways. For example, lithium, sodium, potassium, other members of that first group are all soft, white, shiny metals. Those are similar physical properties. They're not all exactly the same, but they're all soft, white, shiny metals. And they have the same number of valence electrons within a group. Okay, within a period across, that is called a horizontal row. And the elements are not alike in their properties. In fact, they change greatly across a given row. For example, the very first element in a period is always an extremely active solid. In other words, a solid that reacts really, really well. It's very, very reactive. But if you go all the way across the period, you're going to end up with a gas that doesn't react at all. Your noble gases, very different. Okay, if you remember the periodic table I showed you my periodic table, if you remember, the majority of the periodic table was colored yellow. So what does that mean if it's colored yellow? Well, it means it's a metal. The majority of your periodic table is made up of metals. Most of those metals are solids. There are some metals that are not solids. They have melted. But the majority of the things on your periodic table are metals. Then you have this section over here. And I think on your periodic table that you colored, it should be orange. And these are where your nonmetals reside. And a lot of these nonmetals are gases. And then this guy right here, which is like that barrier between the metals and the non-metals, those are called metalloids. So let's talk about our metals. So what makes a metal a metal? Well, first of all, if they're good conductors of heat and electricity. Good conductors of heat and electricity. Metals tend to be shiny. They're ductile. They have tensile strength. What that means is you can stretch them into thin wires. They're ductile. They're malleable. That means you can pound them into thin sheets. They are mostly solids. Most of your metals are solids. One major exception is mercury. Mercury is one of two liquids on the periodic table. Periodic table is made up of mostly solids, two liquids, and then a handful of gases. Mercury is one of those two liquids. The other one is bromine, which is a nonmetal. Your metals can be soft, like sodium, or extremely hard, like platinum. Okay. So what are your nonmetals? Well, your nonmetals are everything your metals are not. So in other words, while metals are good conductors of heat and electricity, nonmetals are not. They're not ductile. In other words, you can't pull them into like thin wires, and they're not malleable. You can't like pound them flat. Metals are shiny. Non-metals are dull. Solid nonmetals are brittle and break easily, which is why you can't pound them because they'll break. They're very, very brittle. Okay. Many of your nonmetals are gases, not all of them, but a lot of them. There are some nonmetals that are solids. For example, carbon. Carbon is a solid when it is diamonds and when it is graphite. Right? It's just packed differently. That's the only difference. It's the only difference between a diamond and coal is basically the way the carbon is packed. Okay. This guy right here is sulfur. And I said there were two liquids on the periodic table. I said mercury was one of them. The other one is bromine. Bromine is right underneath chlorine, second to last column, third row down. That is your other liquid. Okay, then we come to the staircase that you see. Those are your metalloids. So you have two on either side of that staircase. Then you have silicon and boron. Aluminum is a metal. Okay, that's your metalloid. So what is a metalloid? Metalloids are kind of like that transition between metals and nonmetals. They have properties of both metals and nonmetals. That means they can be shiny or they can be dull. They can conduct heat and electricity better than nonmetals, but not as well as metals. They can be ductile and malleable or not. That's where your semiconductors live, at the metalloids. Silicon is one of them.